screening of cancer by actually cancer. And when, by the way, you see a physical sign, whether it's breast cancer or cervical cancer or colon cancer, the probability that this thing is almost 99%. You are actually at stage 4. Therefore, as biotechnologists, what runs in my mind as the basic question towards diagnostics in the future for cancer? It is within micromolecular levels. It is how the cell interacts with the body and interacts with the environment, and it is how you understand the basic morphology and physiology of the cell and immunological reactions that the cell has, where you are informed that there is wrong and right and there is no question in between. And a good child is the one who knows ask questions. It's the same that it extended to the gender and said a good wife or a good woman is meek and does not ask questions. Is that true? It is not true. But does it happen? Do you know it? No. So we need to move to a new paradigm where we teach people how to think and how to search in their mind. Because the first step, when I had colleagues talking about the genesis of this conference on the African International Biotechnology, it started as a small thing. Certainly not as a big thing, because everything starts as an idea in the mind of somebody. And then you extend it and talk to the next guy. What do you think about this? Bonotieno in Kyoto. What do you think about this? And then you discuss, and it grows, it grows. Say, oh, do something about it. Yes. And reminds me of my simple science that we were crystals. And the first experiment we did was to try and grow salt crystal. And we were told that you pick up a small crystal and you embed it in the solution, and this small crystal will attract more substance, and eventually you have a very big crystal. And life is like that. It starts small, it starts with an idea, you plant a small crystal, and it will grow into a mega crystal of repute. Now, to end my welcoming you to Kisumu, I would like you also to think that it's important and it is obligation of the government in Kisumu to create an environment for research and application of research. There is many times we think about research, but we don't think about the application of that research. Research for what? What is the application? It should be application for improving human mind and human welfare. Then we are committed in Kisumu towards partnering for the acquisition of the tools of biotechnology research, and we are also committed to the innovation of the necessary tools and equipment. And the very important thing that the governor emphasizes is the partnership with industry. And the not just industry to sponsor conferences, but also to be placed in these industries, which eventually plays into the economic web of the society for better living. And of great importance is creating a platform for sharing of the information and improving that information. And this sharing, the platform for sharing, can be institutional, it can be across counties, it can be across continents for the betterment of humankind. So, many deliberations for these days in Kisumu. I wish you well, and I will return back to the governor and inform him of the but the world is one big biotechnology. You are the people on the lead, so you are the people to guide us towards a better life. And please, when we are building capacity of individuals, the countries which are here from Europe, from other African countries, and from the Americas, and from the Oceania, from Australia, and also remember that traditionally we have people with indigenous knowledge. They have serious knowledge and biotechnology. Don't keep them blind. And all these countries should work towards a better human race, which solves problems together. And COVID-19 shows that you are part of the world. For example, Europe discovered and America has discovered the vaccine, and at some point we proved everything that was discovered. Little did they know that if they survive and the mutation, which is a technological process, happens where they left behind, the next millisecond to finish it. So, on behalf of the governor, I urge you to also enjoy Kisumu, but think like and legally, and no one should be left behind. Thank you very much.
Thank you, Dr. Rai, for ably representing His Excellency the Governor of Kisumu County. We've taken note of the advices that we've given. The Deputy Vice Chancellor in charge of Partnership, Research and Innovation of Maseno University. Before I give you the opportunity and the mic, I just wanted to acknowledge the fact that
the area for chemistry narrowing down to electrochemistry. So we have some to try. Dr. Nyambera is out. Professor Collins, when the lecturer was speaking, he impressed me. Later, and we recommend that it becomes what we call veterans, goes on part-time. Don't use part-time, which is adjunct or adjunct, and there's another name. There's another name, we'll get it. So, Professor will impress me. So, I recommend that you become a part-time lecturer in the School of Medicine. I will use the facility after we shall discuss. And also representative of the Vice Chancellor. So make one mark as a DVC and also have the speech of the Vice Chancellor. We are ready to you. So first of all, allow me to welcome you to Maseno University and to the National Biotechnology and Biomedical Conference, IABBC. As we have heard, IABBC is celebrating its 5th year in existence in its strides, special strides. To remind you, for the first time in Maseno University, that we are an old university. It was established as a constituent college of Moi University in 1990. Became University the year 2000. The universities that we had, Oceania was number 6. After Nairobi, KU, JKU, Egerton, Moi, etc. We are students, it's like a measure. We have 20,000 students now, 2 campuses, There was Kisumu campus, main campus. When you go to the main campus, I hope you go there. There's three main campus. So we are very proud of our business. They were the representative of the governor. Actually, they mentioned that you are representing the governor. Yeah, indeed, you are representing the governor, Sum County. You talk about how the county government is, destroy the beauty and everything. When you talk about the university, we say that we only invest on the equator. So the equator, after this conference on Saturday, Professor Kolis take to Maseno, so that they take breakfast on the southern hemisphere and take lunch somewhere. So they go to the south, then to the north. So the debate is differently, maybe. The debate is differently. So to remind our participants here, especially those not from Maseno, that our school of medicine is among the best ranked in Kenya, actually number one. There was a board that did the survey and ranked Maseno University School of Medicine as number one. In number 6, but now we're number 2 in Kenya. In Nairobi, they say that there are only 2 universities. The University of Nairobi and others. And also coming to this region, Western region, there are 2 universities. And that's why. And we are not the university of choice. In terms of first years, in terms of choice on their own. But this year we are number 2. Is after which university, Professor? Which is number 1? And JQuat. Maseno. Because JQuat, the 7,000 students, the first 2 years who chose JQuat were 6,800. The difference was small. So let's see. Went to Masai Mara, now I'm on the lakeside. So, welcome, those from JQuat, to Madiza, to Maseno University. You see how we are also doing. And so I'm proud that now, this JQuat and what? And Maseno. We're going to take you next year. So, that is the light touch. So, in keeping that is advanced science for sustainable development in Africa, providing a platform for disciplinary interactions and the scientific exchanges in the increasing areas of biomedicine and biotechnology. And the most importantly, on the current world challenges such as HIV/AIDS and recently the COVID-19 pandemic. Multidisciplinary. Let me go back there. Multidisciplinary. You could write a proposal, individual structure, you get funded by the post and others. These days, the emphasis is on multidisciplinary, multi-institutional, then they talk of north-south. So after that, Professor, what shall we call it? Multi-continental or what? Yeah, because I moved from multidisciplinary, multi-institutional, multi-country, continental. Look for a better one, because that's the way we can survive. So really, I would encourage the deep research, partners or innovations, that let us partner. After this conference, I want to see that we have partnered with so and so, we have partnered from these universities, etc. Joint proposals, student can develop programs, especially in this area. We need those research funds. The IBDC has expanded to become one of the most significant international fora for local international scientists to discuss their research and to build the capacity of young scientists through training and the mentorship. Before this conference, we had the training workshops here to build our young researchers, to equip them with the necessary skills so that they can, right from the word go, know how to develop fundable proposals. But that's when we can survive, and also we can share our knowledge all over the world. Ladies and gentlemen, over the years, there has also been an increase or not. That's not about it. What is that? Well, the technology remains a very promising field as far as application goes, ranging from improving the diagnosis and treatment of hereditary diseases to the development of drugs and vaccines and environment-friendly herbicides and pesticides. As a university, Marcel is committed towards establishing a stronger foundation for science to address the sustainable development goals through training of competent and skilled scientists and professionals. We want to play a role in tackling the second, third, and seventh sustainable development goals and achieve food security, promote sustainable agriculture and healthy lives for all at all ages. Distinguished participants, Maseno University established the Department of Biomedical Science and Technology several years back to be able to conduct research, training, and extension in biotechnology to optimize the contribution of biotechnology and the life sciences for sustainable development through capacity building, innovations, and technology transfer. That department is where Professor Collins Ouma belongs, and we are proud of the department. The research work they are doing, because they are very active, that can be measured in terms of the research funds they raise, and is one of the lead. And we can clap for Professor Collins as a director of the that's cool. We are proud that we continue doing the good work we are doing. We also have a very active director of research and innovations, also headed by Professor Collins Ouma, to support research and innovations within and outside the university. Through such initiatives, Maseno University strives to create high-tech and knowledge-based opportunities in biotechnology and beyond. The university therefore the conference training workshop held for the past 3 days, and the conference has been essential for hands-on training for students to gain practical experience in advanced biomedical technologies, encompassing molecular diagnostics, point of care testing, malaria, control elimination, genomics, and about informatics, finally HIV and COVID-19 pandemic management. As we are told, this conference has brought people from all over the world. If time allows, I can quickly mention the names and where they come from. So scientists, esteemed scientists such as Professor Patkins of University of New Mexico, USA, Professor from University of Pennsylvania, USA, Professor Rubinstein and Professor Laurel of University, USA, Professor Shingo of Nagasaki, University, Japan, Professor Petro from Texas A&M University, USA, Professor Chuk from Colorado State University, USA, Professor Masudi from Uppsala University, Sweden, Professor Akira from Osaka City University, Japan, Professor Eri from Federal University of Technology, Minna, Nigeria, Professor Masahiro from Tohoku University, Japan, Professor Pine from Stockholm University, Sweden, Professor Anam from Royal Institute of Technology in Sweden, and Dr. Anzao from Hitachi Center for Exploratory Research in Japan. There are also Dr. Suleiman from UCSF, Zuckerberg, San Francisco General Hospital, USA, Dr. Kuja from JKUAT, Kenya, Dr. Taro from Osaka University, Japan, Dr. Lines from Badu University, USA, Dr. Kitaka from Mount Kenya University, Dr. Kariuri from Catholic University in Belgium, and Dr. Kawashima from Chiba University, Japan, among others. I say thank you so much and feel welcome. And we are proud to be associated with you. I expect participants to gain scientific knowledge that will find extremely useful, not only in their research area but also in their future career progression. I believe that the experience gained by the students, especially postgraduate students, will contribute to their capacity development and ultimately lead to the growth of science and technology for sustainable development in Africa through collaboration and networking. Ladies and gentlemen, as I conclude, I would like to thank the Kenya government through National Research Fund. These are our sponsors: Hitachi, Japan Society for the Promotion of Sciences, Thermo Fisher Scientific, Beckman Coulter Life Sciences, Agilent, Luminex, Africa Biosystems Limited, Logistics, Biosciences, Signaling Technology, all in to make this Ultralogic Diagnostics, and the local organizing committee, and all the participants that made this conference a success. We also appreciate the support institutions and our organizations, and those include National University, JKUAT, Institute of Primary Research, Cytometry for Life, the Society for Single Cell Surveyor. With those of you who have any remarks, ladies and gentlemen, distinguished participants, it is now my pleasure, humble pleasure, to declare this International Conference, International Biotechnology and Biomedical Conference officially open. Thank you, and God bless you.
Thank you, DVC. And I'm glad you reminded us of what Maseno is. Maseno is the only university on the equator, and what they can potentially try out is to bite an apple on the southern hemisphere and swallow it in the northern hemisphere. So you have to try that out. And thank you for officially opening the conference. Now, we'll move to the next session, and I'm requesting that the DVC and Dr. Rai, you sit through this session so that we will have an opportunity after a few minutes to have a group photo with you immediately after this session. So I hope you'll be able to be with us until the end of this session. So I will be the chair of the next session. And the next session will be started off by Professor Douglas J. Parkin from the Center for Global Health, University of New Mexico, USA. The title will be Elevated SARS-CoV-2 Viremia in Different Ethnic Groups, Relationship with Increased COVID-19 Disease Severity. And I would like to introduce Professor Parkin being the first speaker, in this conference, the 5th African International Conference. Dr. Perkins is a professor of medicine and director of the Center for Global Health in the Department of Internal Medicine. Received his PhD from Ohio State University in 1997 and did postdoc training in hematology at Duke University. He also did other training in malaria molecular vaccine station, the CDC, and research projects in Dr. Perkins' laboratory are based primarily in the US and Kenya. This project focuses on various molecular aspects of the human host immune response to parasites and viruses. The laboratories are also actively investigating the molecular basis of enhanced immune dysfunction in individuals who are infected with HIV and malaria. And additional projects focus on impact of bacteremia on the morbidity and mortality of pediatric population residing in endemic people transmission areas in Western Kenya. So research projects in Dr. Perkins' laboratory involve active collaboration with the Center for Disease Control, KEMRI, Kisumu Ministry of Health, Maseno University, Kenyatta University, Masinde Muliro University of Science and Technology, currently Kirinyaga University, and JUST, Mahidol University, Hospital for Tropical Disease Research, Universities. And then we have Universidad de Valle in Colombia and University of Georgia. The main reason why I'm introducing Professor Perkins is that myself, I was the first PhD graduate of Professor Perkins. And he was my supervisor and mentor several years back. And we have been working together for the last 18 years. Currently, as we stand here, is the program director of the University of New Mexico, Maseno University, Sierra County Referral Hospitals Research Programs, and I'm the deputy director in those programs. So with those few remarks, let's join hands in welcoming Professor Perkins.
Yeah, we were going to plug this in. So I'm going to have to be brief because Collins took up all the time introducing me, okay? So, no, what would the expression be? Collins, he's my firstborn, and I'm very proud of him. He's, I knew him when he was a young guy. He's a full professor now. So it's a privilege and honor. While we're hooking this up here, I've been very fortunate. I've worked in Kenya for the last 20 years, and it's been really fun. I spend a lot of time here. It's my second home. And when I was originally, my first faculty position was at the University of Pittsburgh, and that's actually one of the programs that Collins and some others were in. And then I moved to the University of New Mexico about 14 years ago, and it was to start a Center for Global Health. And so what we primarily do is we work on pediatric infectious diseases, and primarily in Kenya and other tropical settings. We have some projects in Ghana. We use molecular-based approaches, typically genomics. The theme is we study pathogenesis. And then living in the state of New Mexico, very early on in the pandemic, we got a little bit sidetracked. Our hospitals were overrun. When I look at the situation in Kenya, I'm grateful. You all have had some problems, but it's really good that they've not been as profound as they potentially could be. So while it is a serious problem, we all need to exercise caution. On the other end, we got really slammed. So the hospital at the University of New Mexico, I'll show you some pictures here in a minute. It's a very large landmass, but there's only one academic medical center there, and that's the primary referral center. So we'll talk a little more about that. So we were marching along, working on malaria, HIV interactions, and then all of a sudden, as we all know, this thing called the pandemic came to town. So since the start of the pandemic, and one of the things that's funny, I'll just say this really quick, it's kind of fun to give a COVID talk because everyone knows something about it, right? Unless you've been sleeping for a couple of years. And so there's greater than 251 million cases right now, more than 5 million deaths, right? The US has been hit the hardest. Despite semi-strict, and it's different state by state, semi-strict measures, and now a relatively high rate of vaccination. We can talk about that. Tenfold higher than here. And we can talk about that if anyone has any questions on the impact that that's having. And so there's, 40, as of this morning, at 6, there were 46.7 million cases globally in the US, and 758,000 deaths, right? So really the theme of my talk today comes about literally by accident. So being in the state of New Mexico, it's a Hispanic predominant state. So it's the largest percentage per 100,000 of Hispanics in the US. In addition, there is a large American Indian population there, the third highest in terms of per 100,000 in the United States. And so the individuals that we were seeing at hospital when we started to run these studies were from different race and ethnic groups. And because of our geographic location, it's unique in that regard, and that there's a large population of those two primary race and ethnic groups that I mentioned. So, what I'll say from now on is AI and AN instead of, belaboring. Just for folks, and you wouldn't be familiar with this unless you've been to the US and you know the intricacies of race ethnicity. So American Indians and Alaskan Natives are distinct groups. For reporting structures, they're looped into one group. And so although I will say AIAN because that's the way data nationally and internationally are reported, really what I'm talking about today is the American Indian population. And so that particular population has had the highest rate of hospitalization and death, okay? And then the second highest proportion of cases, with the first highest proportion of cases being Hispanic individuals. And so orient a little bit here. Can you see my cursor? Good. So if you look here, that red blob there, it looks like a balloon, that's Albuquerque. Okay, so it's centrally located in New Mexico. If you look down here, that is actually the country, Mexico. Sorry, this is a little sensitive. Over here is Arizona, Texas. So this is the Southwest, okay? If you come to the very upper part of the state right there, where you border Colorado and Arizona, the Navajo Nation is there. And that's one of the largest Indian reservations in the country. So here's what our landscape in New Mexico looks like. It's quite a beautiful place. These are actually the Sandia Mountains there. And Sandia in Spanish literally means melon because in the evening when the sun shines, it's orange like a melon, okay? So let's get to the point. So the hospitalization data in the US, we don't have to focus too much on all of the groups to get belabored on time. But if you look right here in the blue, that is the AIAN population. So as you can see, very high rates of hospitalization. This is data for the US. If you come over here and look at New Mexico, okay, same types of peaks and waves, very high rates of hospitalization. The AIAN group shown in blue there. Look at the axis here, 55, 110. So it's not to scale. So in that particular state, there's even been more disproportionate hospitalizations. Now, let's look at the unfortunate outcome of death. This is data nationally from Race Ethnicity Tracker, CDC. And so in this context, AIAN is shown in the yellow. Okay, so that's mortality with these high peaks last fall. Mortality in the US has fallen because of vaccination rates, but we're starting to see an uptick if anyone has been watching the news, and those are primarily unvaccinated individuals. So once again, data for the US on death, data for New Mexico. In this context, when we look at our axis here, 3.5 times higher. So the bottom line is that particular group has suffered disproportionately hospitalizations and deaths. So the question, why? What's going on? And so we started early on in the pandemic a number of studies. Some were related to drug discovery, some were related to convalescent plasma, and then we're running, and we continue to run, a natural history study. So that's mainly what I'm going to tell you about today, and this is in hospitalized individuals. So the three, we're very fortunate to get funding from the NIH to do this. So really what I'll talk about today is aim one. And the question is, what is the impact of changing viral load dynamics on disease outcomes? Then what one can look at is the host immune response with transcriptomics. I'll show you a little bit of that data. So if one can figure out how the virus influences the host immunological response and identify genes and gene pathways that are important in discriminating non-severe versus severe disease, then that identifies therapeutic targets, which is essentially aim 3. And we'll talk mainly about the viral load data today. So in the interest of time, because we want to give all of our speakers equal opportunity, there's no way to go through that slide. It actually took me at the beginning of the pandemic about 3 days to make. And so the bottom line is there's an interaction between viral replication. So early on, when one gets SARS-CoV-2, those are typically the highest levels of viral load. And those particular viral loads, as you can see here on the bottom, some individuals can have very high viral loads and be asymptomatic. The average period from being exposed, i.e. infected, to actually being symptomatic is about 5.2 days. So what I put here, this is in days, and then these are the clinical symptoms associated. There's quite a range here, okay? But not everyone, but some people progress to, okay. Yeah, as a left-handed guy and moving this and then doing a pointer, I probably just stay with this as long as y'all can see it. So one of the things to think about is moderate to severe disease, right? So you get dyspnea or short of breath and you become hypoxic or not, okay? And then not everyone, of course, but a large proportion, and what we witnessed was a larger proportion of that AIN group went on to severe or critical disease. And that's really the phase that y'all have heard about where there's an acute respiratory distress, there's what's known as a cytokine storm. Those things, although back when we started this, there wasn't much known. There's more known now, but it's still not exactly clear what's going on. So the study design that we employed, right, the inclusion criteria were adult patients greater than 18 years of age. They had a PCR-confirmed SARS-CoV-2 and they were hospitalized for COVID. Exclusion criteria were ECMO, and that's essentially one of the kind of heart-lung machines that you all have heard about, right? So if you are on that at entry, it didn't make sense when you're looking immunologically in circulation and blood. You could not be on ECMO and then progress clinically and go on ECMO and be in the study, but it was an exclusion criteria in the beginning. And so the exclusion criteria were essentially ECMO at study entry, and then either the patients or the legal authorized representative, that is the LAR, unwilling or unable to provide consent. So we began enrollment for this particular study on 4 May 2020, and to date we've enrolled 485 hospitalized patients, okay? What I'll present today are data on 94 of those patients, and they were recruited through 20 October 2020. So just something to keep in mind because you're all experts on SARS-CoV-2 and COVID. Based on that date that I gave you, what we did is we did sequencing of the virus, and so these are pre-variant viruses, okay? So this you could say is the original. I think it was 28 B and C when we sequenced it. Sorry. So here are the sample types we took. We took upper respiratory tract samples. So if individuals were mechanically intubated, we would take a nasopharyngeal swab. If they were not intubated and hospitalized, we take a nasal swab. So that was a mid-nair swab. And then what you can do is you can measure with the PCR reaction that you all are familiar with, you can measure the virus there. Okay? What we also did is we took peripheral blood. And the reason we took peripheral blood is we wanted to see whether or not there was virus. So we used exactly the same PCR test. We wanted to see whether or not there was virus in circulation. It is still debated whether or not that is a live virus. We don't need to get into those dynamics. So the same exact test that one uses to say it's definitively virus in the upper respiratory tract is the same test we use in circulation. Later, if people want to talk about viral viability in circulation, we could potentially do that. So what we did is we collected samples. We collected those upper respiratory tract and peripheral blood samples. Day 0 was enrollment, days 1, 2, and 3, 6, 9, 14. Some individuals would stay longer than day 14. Some individuals that were non-severe would get released before that. Individuals that stayed longer than 14 days if they didn't die, we get a discharge symptom. Okay? So one of the things that I can tell you, you're not intimately familiar with that population. You're all familiar with the fact that there are many different comorbidities, and some of those comorbidities, when we know about the disease severity in COVID-19, are very strong predictors of more severe disease. And so one of the things we wanted to do is look upon baseline. This is when you come into hospital. So this is literally enrollment, right? And so we had, like what I'm presenting today, are 94 patients, 43 of which are in that AIAN group, and then 51 others. And the others were, as I mentioned, based on the dynamics of the state. They were largely Hispanic, right? And then next was white, non-Hispanic, and then Asian and African Americans, based on their distribution in the state in general. Not surprisingly, they're unhospitalized. So one of the things that I can say here is this is of borderline significance, and it's important for you individuals, particularly the students, to think about statistics, right? You make a whole bunch of comparisons, and oftentimes you want to do a correction for multiple comparisons. And that's one of the things that's fun being around students, is that we get to talk about some of these things. And so this right here is not corrective, okay? What it's really telling you, though, is that this AI-AN group is borderline number, okay? If we look at all of those other clinical laboratory measures, the only other thing that popped out, and remember, people were looking pretty similar upon entrance to the hospital, right? And so the neutrophil count was actually higher in the AI-AN group. Prothrombin time, which is something that measures your clotting ability, and then as well as albumin. So prothrombin time and albumin were actually lower in the AI-AN group. So that profile, early on when you first show up, is consistent with other studies in different ethnic groups, stating that when you have a high neutrophil count, it oftentimes is prognostic of severe disease. Low albumin, low prothrombin clotting time, the same. They're associated with severe disease. So one of the things that is common in Native American populations in the U.S. is high rates of comorbidities. And so one needs to look at those comorbidities across all the populations, but particularly when you're comparing the AI-AN versus the other groups, okay? And what I can tell you, the bottom line is, even though the literature supports high rates of, for example, diabetes in the AIN population, when we looked in this hospitalized patient population and compared the AIN versus the non, i.e. that all other group combined, you actually see a lower rate of cancer, right? Lower rate of coronary artery disease, lower rate of heart failure. And then the other ones that are important, things like BMI and then classifications of BMI. Diabetes, those were not different between the groups. In fact, if you take the mean of the comorbidities, what you find is that the AI-AN group actually has a lower mean comorbidity, okay? So the take-home message from there is you are comparing one group versus another group. The other group is the aggregate group, right? But when you look at their comorbidities, a little less in the AIN population. So if I were to tell you they had more severe disease, and you said yes, of course, because they have more comorbidities, that's the reason we did that, and that is not in fact the case. So then we looked at clinical events that occurred during hospitalization with severe disease versus non-severe disease being defined on whether or not you went to the ICU. And so the setup in the US, there's different amounts of external oxygen delivery, and there's a scale set up, and you can classify disease severity with that. A more clean break point, because those things are decision driven by the clinician that's treating the patient. Yes, they're physiological parameters, but they're really human decisions, right? Whereas when an individual is in ICU, that's where you have to be for the mechanical ventilation. Also, when we look back at that systemic inflammatory response, when we think of COVID-19 in terms of its disease pathogenesis, right? There clearly is a systemic nature to that disease. And so that oftentimes will lead to shock, and those individuals need to be managed in ICU because they need pressors, okay? So these are the acute events that took place during this 2-week period. So if at any time during your 2-week period to cluster groups into severe disease, if at any time you went to the ICU, you got classified into that cluster of severe disease. If you did not go to ICU throughout your 2-week stay and or get discharged prior to 2 weeks, you're in the non-severe group. So that creates, for statistical comparisons, an effort and never group, okay? We also look day by day to see when you go in and out of ICU and what your immunological response looks like. But for this data here, when we think about viral load, let's think about severe and non-severe disease. So what you see down here, nearly an equal distribution of males and females in that AI-AN group. Now remember, data globally shows that in general it's not a super strong signal, and it's different in different populations, but males tend to be more effective with severe disease.
So if you think back, the AIAN group is a little younger, and they have an equal gender distribution here, right? And then if you do this proportional comparison here, what you find is that the AIAN group actually had more severe disease, okay? If you look at length of stay, how long do they remain in hospital? So remember, we're collecting samples for 2 weeks. The people stay in hospital longer, and we know that, right? So our immunological and viral measurements are across 2 weeks. We know how long someone stays in hospital. So the length of stay was twice as long in the AIAN group. In this group of 94 patients here, the day 14 mortality is essentially the same, okay? What I can tell you in the larger group of people in this particular population, and when you look past 14 days, mortality in the AIAN group becomes significantly higher. And so if you think about the fact that they're staying around hospital twice as long, unfortunately, not in all cases, which is good, but in some of those cases, many in fact, the final outcome after that protracted hospitalization is actually mortality. And so when we modeled this, one of the things we wanted to know is, what are the predictors of disease severity? So I want you to think about all of the stuff that I've talked about. So this is a forward-backward selection model, okay? So here are the variables in the model. So one way to think about this as students is you put everyone in a cage match and you let them fight it out. And then whatever emerges as the top predictors or the top fighters are what gets reported in the output of the data. And so if you put in race, ethnicity, sex, pregnancy status, age, asymptomatic prior to enrollment, because you want to control for the amount of time someone's been sick, body mass index, and then treatment, which is something we haven't spoken much about. So patients would get remdesivir and or steroids, so that goes into the model to account for differences in disease severity based on treatment. And then a group of people out of the 94 that had greater than 5 comorbidities, because you didn't want to represent rare events, okay? So if there were greater than 5 individuals for each of those comorbidities that we spoke about, you go in the model, okay? Now you understand the modeling. When I show the others, they'll be more straightforward. So what you see here is this significant, I put that asterisk there because these particular models are corrected for multiple comparisons with Holm-Bonferroni, okay? And so the bottom line is the top predictor of disease severity is ethnicity, race/stroke ethnicity, and in particular, the American Indian stroke Alaskan Native group have the highest rate of severe disease. Gender was next, right? Being male, okay? And then steroid use. Later, if you want to talk about steroid use and the increase susceptibility to severe disease, we can talk about that. Mainly what that means, and that's what these models will show you, okay? Many of the patients that are more ill get treated with more medication in this particular context, particularly early on, different types of steroidal preparations. So they're more ill, so it's not surprisingly that it's associated with an increased severity. So really what I want to show you here is looking at exact viral loads. There's not very many studies that have done this. This is the log-based 10 copies per 100,000 cells. So I don't want to belabor the point too much, but as students, what I want you to think about is this. If I take a swab, be it a nasopharyngeal or nasal swab, and then I measure a virus there, this is the PCR reaction, and you get CT values, okay? And then I want to compare you, put you in a group and you in a group. The issue is, how good a swab did I get? Did I really dig in there? Did I not go deep enough? How do I know how much virus I got? So these reactions that we're using, there's something in the denominator, and it's a human gene. And so you can standardize X amount of virus per X amount of human material, and then that's what the 1,000 cells is. There's like 53,425 copies of RNA-seq per cell, so that's how the 100,000 is there. So the bottom line here, really, is if you look in the upper respiratory tract, okay, what you see is, in non-severe individuals, you see a little higher viral load in the non-AIAN group, okay? And really only on day 3. But not a big signal. What I want you to concentrate here is this is a way to cumulatively say, across all those days we looked at, this is really the summation of group 1 versus group 2. That's the important one. The other shows the day-by-day dynamics. but the really important one is the last one here. So in non-severe disease, there's no group. There's no difference in those two groups. If you look in severe disease, so remember, increased viral loads in the upper respiratory tract, and some studies say in blood, are associated with increased disease severity. Complete overlap. No dissociation at all between the groups. So the conclusion is viral load in the upper respiratory tract in either non-severe or severe disease doesn't explain much of what's going on with the pathogenesis of severe disease. So this is the signal that we found that was really interesting. If you look in peripheral blood, no difference across time, cumulatively, okay, between the two groups. However, if you look in individuals with severe disease early on in the infection, the AIAN group has much higher levels of virus in blood, stays around for a couple days, and then cumulatively across time, and these are corrected for multiple comparisons, you have a significant difference between the AI and non-AI groups. So the modeling that you're now all experts on, we wanted to say, okay, first we looked at comorbidities and all of those other things. What else can we put in there? How about a viral load in the upper respiratory tract and viral load in blood? And what you find when you put all of those things into the model, along with what you already know, the mean viral load in blood was the strongest predictor of that giant list that you're now familiar with. So virus in blood is a strong predictor of severe disease. 2 times 10 to the minus fourth, significant after multiple comparisons. Male pops out again, right? So it's bad to have virus in your blood, and it's bad to be a dude, I guess. And so the other modeling that we did was a multiple event per subject. It's a conditional hazard model, a Cox proportional hazard model. And what that does is it sets up when you became symptomatic until, quote, an event. The event is defined by time from that standpoint, when you became symptomatic, to the first and then subsequent detection of virus in blood. And so when you run that particular model, what you see, the group of individuals with the highest rate of virus in blood, and then we could talk about those other things later, but I want to get through this. The bottom line is that is a very strong predictor, being American Indian stroke Alaska Native, of having virus in blood, right? What I want to tell you about now is what does that mean immunologically? And as you can imagine, in a 20-minute talk, there's no way for us to go through this. So I'm going to hit the high points. Really what this is transcriptomics. And this is the entire expressed transcriptome, okay? And so what you do, this is next generation sequencing. You use a library preparation, so you go in and it sits down on the poly A tail. So expressed genes, mRNA, you capture all of those. You get more than 50,000 readouts, which when you run it through informatics pipelines gets, and in our case, in these data sets, about 22 to 23,000 genes. And so really what you're doing is a case control comparison. So I just showed you that this group has more severe disease, this group has more virus in blood. What's the impact immunologically? If we take that blood and look at it and do transcriptomics, so this is a case control comparison. This is a subset of individuals. It's about 40 individuals. And so it's AI, AN versus others. And so what emerged, because there's no way to read that in the interest of time and space, right? If you look at those little thermometers right there, the thing that's tricky, so we don't want to get in the weeds, remember this program auto sets, right? So when it sees data on a day, it calls it 1, 2, 3, 4. But remember, there's day 0, which is actually number 1. So the real point is, early on in the infection here, right? Red means there's an increase in gene expression, blue means there's a decrease, right? So what you saw there in that AIAN group is you saw increased furin expression on days 2 and 6, okay? And one of the things to keep in mind is that furin actually facilitates the SARS-CoV-2 entry, i.e. endocytosis into the cell, okay? This is a different pathway map. There are currently 3 pathway maps in Medicore for COVID-19. This is another one. This is immune dysregulation that's been annotated, okay? What you see here is, and this was really the strongest signal in many different algorithms and systems we've used. So human leukocyte antigen, HLAs, which compose MHC class II, i.e. are immunological receptors of how well we process antigens. And that AIAN group is actually early on And then a little later, there's a class of those HLAs that are downregulated, okay? Interferon alphas, some of you that have been following the virus, right? When we think of the interferon alpha pathway or interferons in general, particularly the alpha lineage, they help us fight viruses. SARS-CoV-2, you would think increased levels, right? Because that's the natural response to viral infections. So what you see in that AIAN group is downregulation of interferon alpha, as well as interferon alpha 3 and also interferon alpha 4, right? And then studies have shown that when that is downregulated, not in these particular populations, but in other populations, it's associated with severe disease, right? Conversely, interferon gamma was upregulated. So when that particular inflammatory meter goes up, other studies have shown that that is, in fact, prognostic of poor disease outcomes, i.e. More severe disease and more mortality. And so the bottom line is, those signals that people have seen in other populations are enriched in the AIAN population. And so, let me hit the high points really quick. There's comparable comorbidities, yet more severe disease, right? SARS-CoV-2 in peripheral circulation is higher in the AIAN group, right? One of the greatest risk factors for SARS-CoV-2 in peripheral blood was AI ancestry, right? And so, in addition to that, the host immunological response from those same samples measured on the same days where we detect the virus, there's dysregulation in immunity, and that dysregulation in immunity follows a pattern that's more similar to severe disease. And so I really appreciate all your time today. I want to thank the team. And this is what we've been doing back on the other end for a couple of years. And so thank you so much for having me. Cheers.
Yeah, you might want to spray that, right? Particularly when you look at these pictures, right? Now, don't be scared. I've been vaccinated 3 times and only had COVID twice, so we're good.
Thank you, Professor Perkins. Can we just get one burning question? I see a hand there.
Thank you very much, Professor Douglas. My name is Sarah Suleiman from Institute of Private Research. Allow me to ask 2 questions. The first question is, you looked at SARS-CoV-2. Did you differentiate the different variants that are there in SARS-CoV-2? Then the second question is on genetics. So I'm looking at the population, and in one of the population, there was a high risk of that population being hospitalized. Kindly make comments in terms of patients' genetics, if they have or play a role in regards to SARS-CoV-2 infections.
Yeah, no, you ask really good questions. Thank you. In this audience here, I can probably speak more freely than I can on the other end, okay? Just because of different races and ethnicities, different individuals and populations and groups feel different about genetics, okay? And so I can answer your question. On the other end, one has to skirt around and tread very cautiously, is the truth, okay? So with the virus, on the date at which we stopped, it was late October 2020, okay? So we sequenced the virus in these individuals and then continued to sequence it. I think we're up to like 485 patients, okay? These individuals that I showed today were all for non-variant viruses, i.e. the earlier lineages of the virus. So it was 20, depends on the nomenclature system, but the one we were using, we used all 3, but it was 20 A, B, and C, okay? So this was pre-Delta. And you ask an interesting question, and I won't get too long-winded, but what we would do is we would go in, we would spend most of the day in the hospital recruiting people, getting samples. Then we would go back and, dress in the Pampers and the tie-back and then isolate those samples and run experiments. And it was interesting. It was Saturday evening, and one of my colleagues, this individual right here, this is Ivy Hurwitz. It was Saturday evening, and she comes running out of the lab, and she's like, "Dude, you got to see this." Yeah, okay, sure. And what it was is the viral load was really, really, really high in this patient. And then
well, everyone that followed, so we thought that there was an error. And the point is, and that's interesting for you guys to know, that's what's cool about being in the lab and doing the clinical medicine as well. So what it was, we didn't know it. That was the first case of Delta in the hospital. So we read different things about the pathophysiology of the virus and how it binds to ACE receptors, but the truth is that is so highly transmissible because your viral loads are off of the chart. So these people here, even though they have high viral loads and one sees it in blood, we're really excited. That's what folks are doing on the other end right now, is after we have the variants that came to town and spread like wildfire like they did here, we're looking to see viral loads both in circulation and there. So then what we'll be able to do is answer your question and say, here's the normal old nasty virus, here's what happens when it gets worse, okay? Genetically, it's tricky because there's not that much genetics that's been done in the AIAN group. But what I will say, which is honest, we are a product of our ancestors, right? And immune response genes are the most enriched of all of the genes in our system. And so one way to think about it is when we are in a particular region for a long period of time, and let's say, for example, something like smallpox comes in, that particular populations, literally, it's multiple populations of individuals, those American Indians, were highly affected by smallpox. I didn't know this because I'm not really a virologist until COVID came to town, and I'm still not a virologist. But the truth is, I didn't realize this, the 2009 pandemic flu had a much higher rate in that particular population as well. So clearly there are genetic underpinnings in all of us, and those things tend to cluster into race and ethnic groups. There's a study that came out, what's today? Thursday, last Friday, and it's really interesting for any of you that are interested, right? It's actually a receptor, and it's on cells in the lung. It's not an immunological response gene. That particular receptor, it came up in a gene loss that was a hot spot, it's in region 3, chromosome 3. And what you see is this cluster of genes. Those genes, as an answer to your question, are different in different populations. So Southeast Asian is how they classified it. So we say Indian, you guys maybe say Asians, versus our American Indians, right? And the point is, that population, which has also been hit very hard with severe pathogenesis, severe disease, there's a 69% homozygous frequency of that particular polymorphic variant in this LT gene. And the heterozygous is like 13%. So those things, and it won't just be that gene, it'll be clusters of genes. Those things truly explain the differences amongst race and ethnicity. So thank you for the question. Thanks.
Thank you, Professor Perkins. I'm sure you'll be here with us the whole day. So that's, I know there are a couple of questions where members want to ask a question about. So get in touch, link up with Professor Perkins, and let's give him a final applause. Thanks for the presentation. So our next speaker is Professor Akira Kaneko from Osaka City University, Japan, and Karolinska Institute, Sweden. So Professor Kaneko is a professor of global health, Department of Microbiology, Tumor and Cell Biology, Karolinska Institute in Stockholm, and a professor of parasitology, Graduate School of Medicine, Osaka City University. Sorry about the technicalities. Okay. Apologies. He has held the position of adjunct professor, Institute of Tropical Medicine, Nagasaki University, Nagasaki, among other institutions. He has won several awards and recognition, including the TropMed Outstanding Alumni Award by Mahidol University in Thailand, the Tropical Medicine Award by the Japanese Society of Tropical Medicine, Japan, among several other awards. Importantly, he now leads the SATREP project focused on sustainable malaria elimination in Africa. He has done extensive research in Homa Bay, just a lecture, and is well conversant with the malaria situation in the Nyanza region. He's a fluent speaker of the Luo language, so don't talk Luo around him. So I take this opportunity to please join hands in welcoming Professor Akira Kaneko.
We are Oceania. But I'm not a really fluent Luo speaker. Thank you very much for inviting me to this opportunity. Today, I'd like to introduce our recent project, SATREP's malaria elimination in Homa Bay County. And we have already conducted a workshop in the last 3 days, and many technical issues already discussed. No. Now, I'd like to start this slide. This is Vanuatu in the Oceania. So where I started work in 1987. So in the last 34 years, I'm involved in malaria elimination project. So then, my key thesis is the power of community is key for sustainable malaria elimination. So then, in Oceania, only 3 countries malaria endemic. That is Papua New Guinea, Solomon Island, and Vanuatu. But there are many islands and island nations in Oceania. But why only 3 is malaria endemic? That is this southwestern part of Oceania. So I cannot give you direct answer, but I like to give you some background. That is how human and malaria parasite and mosquitoes settled and distributed. This is a latter scenario. So anthropologists say there are 2 human waves in human settlement in Oceania. One is near Oceania, like New Guinea or Australia. That's a very old human settlement. That is about 40,000 years before present. But small all Polynesia and Micronesia, that is only 4,000 years before present, human is settled. So then, that up to Easter Island, but malaria is limited by this backstone line. So this is actually a limit of Anopheles mosquito breeding. So east side of this line, no mosquito. So that's a very special place. So I can say Vanuatu is a unique malaria island in remote Oceania. So this people in remote Oceania is called Lapita population. So they speak Austronesian language and they have a special deletion in mitochondrial DNA, and they made Lapita pottery. And they saved and settled some part of island Southeast Asia. Jared Diamond, they called this process Rapid Express Train in Oceania. So now the malaria situation in PNG, Solomon and Vanuatu from WHO report. Please note very high mortality in very small population, but high malaria deaths. So maybe this part of the only place outside Africa still people are dying of malaria. And Vanuatu is rather low parasite incidence. I like to tell you, so in about 30 years ago, Vanuatu situation is like Papua New Guinea now. And then you can see the switch from Plasmodium falciparum to Plasmodium vivax. So New Guinea half and half, Solomon is 78% is Plasmodium vivax, and Vanuatu is 94%. So this is the way Vanuatu also experienced in the last 3 years. So I'd like to focus a little bit about Plasmodium vivax. First, distribution of endemic area is very different. P. vivax, falciparum. That is, as you know, no P. vivax in this tropical Africa. And this one we now know, Daffy native population in tropical Africa. So vivax parasite cannot invade to red blood cell without this Daffy antigens. So then, what is the difference in life cycle in Plasmodium vivax? I like to point out several things. Of course, first is vivax has hypnozoid, and they make relapse 3 months or 3 years later infection. And also vivax is infected only young red blood cell called reticulocyte. And also falciparum, trophozoite and schizont, they are sequestered in the endothelial cells of deep organs such as brain or liver or kidney. But vivax doesn't do that. So then, one important is timing of gametocytes. Vivax gametocytes appear very early stage of infection, usually before symptom or treatment. But P. falciparum gametocytes appear late, usually after symptomatic and treatment. So in this difference, make vivax less severe and less resistant to drug. These are this pointer somehow I can't control, but don't worry. So this is a simplified life cycle. And disease caused by erythrocytic stage. But for elimination, malaria elimination, this relapse hypnozoite and also P. falciparum gametocyte. These two stages are quite important. And available clinical drugs like quinine, chloroquine, or mefloquine or artemisinin, all kill the parasite in erythrocyte stage, but not effective for P. vivax, hypnozoite, and P. falciparum gametocyte. Then this primaquine is an important drug for these stages. So now, primaquine used for malaria elimination is again focused. So this is a very old knowledge. These drugs were developed in 1950s, but now it's focused again for P. vivax, hypnozoite and P. falciparum gametocyte. And this one is also important containment of drug resistance. And we know it's a problematical side effect, that is acute hemorrhagitis in G6PD deficient individuals. And PVAX need 14 days treatment, so this problem is much severe. But pifalciparam is single dose of primakin is effective. And now, conventionally we use 0.75 milligram per kilo, but now WHO recommend 0.25, and we use further low dose, that is 0.15 milligram per kilo. And G6PD deficiency prevalence, global prevalence, support so-called malaria hypothesis. And then this is a Vanuatu archipelago. This is an amazing place. The population is only 200,000. But there are 120 language groups on 68 inhabited islands. And this is I already mentioned Buxton Line. So island is small and isolated, but the community also isolated. And mountain, the island is volcanic origin, and high mountain and uncontrolled river create a breeding site of Anopheles parauti. And the people are living quite peacefully, and often depending on own agriculture. And we saw many malaria cases previously, some fever, severe anemia, and sometimes cerebral malaria. And P. falciparum and P. vivax show seasonal fluctuation. And P. falciparum fluctuation is very clear, but so this is a P. falciparum, but the P. vivax is not much. This is due to hypnozoid of liver stage. This is the age-specific prevalence of P. vivax and P. falciparum. So at the birth, no parasite, but P. vivax prevalence increase very rapidly and quickly, and start decreasing. And P. falciparum is followed after that. And this shows annual parasite incidence by island and G6PD deficiency on island. So we can see clear correlation. So this Vanuatu Islands support also that's malaria hypothesis. So then Aneityum Island. This is the southernmost island in Vanuatu, and when I visited the first time in 1991, population is only 718, and the P. falciparum and the P. vivax are prevalent and show the marked seasonal fluctuation. So as a WHO malariologist, I like to try and test feasibility of parasite elimination on this island. So then I started the Aneityum project in 1991. And eventually I showed malaria can be eliminated on isolated island by well-adapted short-term mass drug administration and sustained vector control, if there is a high degree of community participation. So in 1955, first global malaria eradication program is initiated. But many African countries are not actually included. But this program is heavily reliant on DDT spray, and seized in 1969. And world community, international community learned no magic bullet and no plan to fit for all for malaria elimination. So then in 2000, around 2000, new international commitment to global malaria eradication program is started. This small Aneityum island provided proof of concept of malaria elimination. So what happened on Aneityum after that? So about P. falciparum, it disappeared after first malaria mass drug administration, and never come back again. But P-Vivax, we got one resurgence in 2002, but it's contained again, and then sustainable freedom from malaria is maintained up to now for already 30 years. And this is a mass drug administration regime at that time. So it's to cover the total population of our nature, and once a week for 9 weeks, we use primaquine, chloroquine, and fansidar. So this is a time before the artemisinin era. With this, to result in a malaria-free human and vector population on the island. So this is a really community-based operation. At that time, Vanuatu is a poor country, but also 1991, malaria control program itself is very limited resources. So then this drug administration and bednet impregnation with pyrethroid. And bednet is used at least 10 years at that time. And there is a human movement by small brain. So we set up surveillance by community microscopists. And this system is maintained quite a long time up to now. So one important thing is malaria is disappeared, but people are still using bednet because obviously there are mosquitoes. So this part is very important to prevent resurgence, I think. So then recently, malaria is disappeared gradually, especially in south part of Vanuatu, almost reached to elimination. And then this graph shows, but Bivax malaria is remain. So this is our cross-sectional survey, 1980s, 1990s, and 2010s. So 1980s annual parasite incidence is 180 per 1,000 population. That is the current level of Papua New Guinea. Then that is gradually decreased. So now it's 13. So then by microscopy, prevalence by microscopy also decreased from 12%, 6%, and almost 0%. And only Bivax is remained. But by PCR, 2010, still 2% parasite prevalence is remained. And all of them, or almost all of them, are Bivax malaria. So there are still remained parasite spots, especially in north part of island. So we are now proposing PCR-based enhanced surveillance system in Vanuatu. So then this COVID-19 came to 2019, and Vanuatu itself only 4 confirmed cases of COVID, so new. But they closed the border completely. So I'm really worried what is happening in malaria. So then, from 2000, money to endemic countries is increased dramatically, such as Global Fund or PMI. So then, number of malaria deaths globally first started declining around 2003. But still, 400,000 people are dying of malaria, and 90% of burden remains in Africa burden. So UN SDGs put to end malaria by 2030, but the feasibility of eradicate malaria in tropical Africa, this is the most important challenge, I think. So there is still strong malaria band in tropical Africa, and our project site is Lake Victoria in this Homa Bay County. So then in this area, there is a still pernicious circle between puberty and under 5 mortality is continued. So then we have already very good tools, malaria control. That is LLIN, long-lasting insecticide treated bed nets, IRS, indoor residual spray, and RDT, rapid diagnostic test, ACT, artemisinin-based combination therapy, and IPTP, intermittent prophylactic treatment for pregnant women. But why does high malaria transmission continue in this Homa Bay region or lake region? So in our project site, we have a small island and big island and the mainland. So then we start our malaria survey activities in 2012 in communities. Then I like to show some characteristics of malaria transmission. First, high and heterogeneous malaria prevalence. This is a prevalence by PCR. In mainland, it's very high, highest. Small island is rather low, and large island is intermediate. This is the age-specific prevalence. This is age, and PCR microscopy. And this part is represent asymptomatic and submicroscopic infections. So this is a really large part, including adults. And we conducted the pilot MDA studies on Okode Island. That is a small island in the Lake Victoria. And this is a PCR, and this is microscopic prevalence. And we use ACT and single low-dose primakin. And by microscopy, parasite is disappeared completely, but resurgent within 6 months. So this result is shown. It's really, we need a strategy for sustainability. That's very important. And also, vector is a very strong transmission. So this shows high entomological inoculation rate in this Lake Victoria. This entomological inoculation rate is the number of effective mosquito bite per person per year. So this color dot is our communities. So then this EIR is estimated from seroconversion rate, which is calculated from age-specific pattern of seroprevalence to malaria parasite. And our Korean entomologist, Professor Minakawa, is observing, reporting species shift of vector mosquito. That is from Anopheles gambiae to Anopheles arabiensis. And this Anopheles arabiensis is a pyrethroid resistance and exophagy. Exophagy means outdoor biters. So previously they are biting indoors, but now they are start biting outdoors. So then, this is a catalog of how people utilize mosquito nets. So massive mosquito net distribution is conducted since 2006. So not all people are using mosquito net like this. So it's a really multi-purposely mosquito net are used. So we defined 3 major programs in residual transmission for malaria elimination in this area. First is asymptomatic submicroscopic cases. So they neither seek the treatment nor are detected, but still maintain the transmission. And second is pyrethroid resistance, early biting and exophagic vector. This is a resistance. They are resistance to available vector control tool, like LLIN or IRS. And number 3 is inappropriate human behaviors. So alternative use of bed nets or delayed diagnosis and treatment, and finally, lack of ownership of program. So to solve this problem, we still need innovative and sustainable approaches. So then, we started SATOREPS project in 2020. That is a JICA and AMED supported program. And myself is a Japanese PI, and Dr. Jesse Gitaka, Mount Kenya University, is a Kenyan PI. So concept is like this. There is a glacier in malaria endemic area. People are dying of malaria. That is only part of problems. But underwater, mass of asymptomatic cases, and they, including adults, and they become source of infections. So for this, we need medical intervention such as MDA or improvement of diagnosis and treatment or vector control. But together with this, we like to propose intervention for human behavior changes as socio-economic approaches. So as vector control, we like to test novel vector control tools. That's Oriset plus seeding nets. Oriset plus is a new class of mosquito nets that is contained pyrethroid plus PBO. That's effective for pyrethroid resistance mosquito. Then we specially ordered shingling net with this Oriset plus materials. And we expect this net can protect this population, the school children. So they are actually highest malaria prevalence in age groups. So then as human behaviors, we have two pillars. One is behavioral economic intervention, and second is the citizen science approach. On the top of knowledge enhancement, we like to test a conditional award if non-infection is proved. And we have two schemes, that is lottery incentive scheme and conditional cash transfer. So that is small chance but big money, or even chance with small money. So which is more effective, we like to test. Along with field intervention, we have a research agenda in SATOREPS. Pharmacogenetic aspect of antimalarials, which one is Hiratsuka in Tohoku University. He will talk, I think, tomorrow about this session. And also parasitogenetics and human genetics, and Professor Tane, London School, already talked in the workshop. And now we have a Kenyan SATOREPS PhD student in Osaka City University. Protas and Kevin is already arrived last year and working very hard day and night. And Protas has a poster in this session about a very interesting study about mixed infection. So please look at that. And Grace is coming to Osaka soon. And also importantly, so Jesse Gitaka is a PI in Kenya. So he, in his place, various young Kenyan researchers who obtained PhD outside is, so now it's come back to his place and become a research hub in Kenya. And this is, I think, is very important for sustainability of research and approach. Obviously, malaria elimination is a long term. So then, in Homawe Hospital, we have a setting in field laboratory. And there, we have already tested novel malaria diagnosis based on flow cytometry. And this become a platform of knowledge transfer to local staff. And then in Bita, this is within Ishipe, we have a SATOREPS project office. And Wataru and Makoto, two Japanese scientists, is settled in this place. And Wataru will make a presentation, I think tomorrow, about malaria situation in this our project site. And finally, COVID-19 and malaria, this interaction is becoming a new project, new subject in research agenda. So we like to address this issue also by health policy and human behavior, and also parasite and vector genomics. And this new subject is supported by Hitachi Fund support. So my final message is, so this is a community health frontier. That is a very important part of health system in Kenya. So the power of community for sustainable freedom from malaria. So thank you very much for your attention, and also this grant support from community members and all staff and students, and SATREPS VR is about the Vanuatu part, Vetenskapsrådet in Swedish, and the Hitachi Fund support. Thank you very much.
You can just hold on, Professor Akira, for just only one question for Professor Akira. Yes, can you pass the mic to her, please? She's hiding behind the pillar, so.
Thank you, Professor Akira, for the great presentation. We appreciate the great strides which have been made in trying to eliminate malaria, but maybe insect lovers will forgive me, because I'm thinking, as long as we have mosquitoes on face of the earth, we'll always have malaria and all these other viruses, Zika, dengue, and all these which mosquitoes carry. Why aren't there projects trying to eliminate the vector? Because if the vector is there, the disease will always be there.
So about malaria, we had malaria in Japan, USA, and even Europe, up to Finland. We had malaria transmission, but malaria is disappeared or eliminated. But still we have a mosquito, anopheles mosquito, even in Japan. So I think it is very possible. So malaria elimination with anopheles mosquito, about malaria. So then, to killing all anopheles mosquito, that was actually concept of first malaria eradication program in 1955, I mentioned. But that is, at this point, it's not feasible and not so good idea. So that's why we have more approach to human side and communities. So of course, suppress anopheles mosquito is very important, but in our trial, mosquito can be suppressed something like up to 20%, but the last part is always remained, and that small number of mosquitoes is still enough for malaria transmission. That's why killing all mosquitoes, if only that strategy is not a good idea. Is it all right? We can discuss more later. Thank you very much.
Thank you. Let's give Professor an applause. See, so he's speaking Luo. Luo is, for those who don't know, Luo is being spoken by 90% of people around the Lake region. It's the dominant local dialect here. So our next speaker will be Dr. Sarah Suleiman from the UCSF at Zuckerberg, San Francisco, then hospital in the USA. Dr. Sarah is an immunologist by training with a focus on understanding risk of progression to active TB disease and developing predictive biomarkers. She's currently an assistant professor, Division of Experimental Medicine at UCSF and the Zuckerberg San Francisco General Hospital. She was an instructor at the Brigham and Women's Hospital and Harvard AIBB's 2021 Medical School, where she focused on dissecting host factors associated with TB risk, including genetic association and T-cell responders. She opened her lab at UCSF in October this year. So let's join hands in welcoming Dr. Sarah Suleiman for this presentation. The presentation will be via Zoom, so.
Yes, sir. All right. Are you ready? Can you hear me? That's what the line is. Are you okay? She's smiling back. I'm trying to see. Okay, just a minute. I'm going to try to carry this out. Oh, it's here. This guy's down. So, can you hear me? You're not on mute.
Check your microphone really quick, bottom left. Microphone. Make sure that the source of the mic, there's usually two, is set to the appropriate setting.
Wait a minute. How does it work now? Hello? No response? Yes. Yeah, yes, I can. Can you hear me? You can, right? Okay, then we are good to go. Only I need to connect to the speaker and then we're done. So, perhaps we will hold this here correspondence. Okay, are you good? I want to try to connect to the speakers. Just a second. So who is coming to connect to the scriptures?
So wanted to take advantage of the hybrid system where we have face-to-face and also people joining via Zoom. So sometimes we will see us transitioning into this type of technology, but just bear it with us.
Sarah, can you speak? Yeah, we can. One second, we are trying to connect you to the speaker and it seems to be a bit of a problem.
Once you hook the external speaker,
You're going to connect to the external.
yes, you can then go back in the settings in Zoom and you have to select that speaker, just like we did with the mic.
You need help with the IT guys, but well, we are sorting it out with the IT guys. Just hold. seeing when we get the sound going. This was. What does it do? Didn't go in there with the connection. Sarah, can you try to speak in something, please? I just want to. I think we're going to go with this. That's what we do. Yeah, just go ahead, please. What is it? Can you go ahead? No, it can't because this is a little. It's not getting the sound from outside. She's been reading for like hours and for Oceania. She has to go to bed. It's 11. Sarah, are you connected? No? We have lost her. Oh, this Wi-Fi, is it really steady? I told the lady to pay the charge after they're paying it's Oh, we're back. So we're going to try to take your sound from the mic, if that works. Okay. Yeah. Thanks. So let's get going. I know it's late on your side, so we don't want to keep you waiting any longer. Please go. I'll hold it. Okay, Sarah, please. You can't hear me. You can't hear me. Can you see my thumb? Can you speak? Goodness. Trying to go and throw me on our side. No. Can you say something, please? You are speaking, but I can't hear you. Problem is, I can't hear you. But you can hear me. Can you do this if you hear me? Okay, good. God. Oh, that's a great one.
one has been before.
Oh, good. Go ahead. Just leave it here. We can pick your sound now.
Okay, great.
Perfect. Thank you.
Hey!
Hey, let's get going.
Okay. Let me know when to start.
You are ready to go, please.
All right. Okay. So, Habari za asubuhi here. Thank you for inviting me to speak at the conference. I'm sorry I couldn't be there in person and clearly created some issues with the hybrid meeting format. So as mentioned, I work on TB, and my main focus is understanding mechanisms of progression to active TB disease. So I'm presenting an ongoing project integrating genetic and transcriptional profiles of innate cells in order to understand mechanisms of TB susceptibility. I just started my lab a month ago, so it's an exciting time. So as many people in this audience know, TB is still a huge problem. So the incidence of TB actually was higher last year because of all the interruptions to TB services that were introduced by the COVID pandemic. And the estimate is that about 1.5 million people actually died from TB disease as of last year. And there's debate about whether the mortality from TB is lower or higher than COVID, but the COVID notifications are much higher, so there's actually a chance that undiagnosed TB cases and deaths actually exceeded COVID over the last year. And one of the main epidemiological issues with TB is that there's a large reservoir of latently infected people, so people who have been exposed to Mycobacterium tuberculosis but haven't progressed to active TB disease. And the estimate is that about 1/4 to 1/3 of the globe is actually latently infected with MTB. So the main that my research addresses is what's unique about the people who actually progress to active TB disease. Since the majority of MTB-exposed people never develop active TB, I focus on the 5 to 10% who have a predicted lifetime risk of progressing to active TB disease. And since people in the same communities were exposed to the same circulating TB strains, have a different risk of developing TB, that leads to hypotheses about host-specific factors that are involved. One hypothesis that I've been recently thinking about is whether host genetic factors actually differentiate individuals who are at risk of progression to active TB disease. So to address the question of genetic susceptibility to TB, one approach is to take a genome-wide association study. So just introducing what genome-wide association studies are, you have groups of cases and controls for the disease of interest. And you genotype individuals, so you identify all the genetic variants that are present in the cases and the controls. And what you want to look at the individual locus level is whether there are specific alleles that are enriched, for example, in people who are cases, compared to the controls. So in this case, we have an example where the A genotype is associated with a higher risk of the disease compared to the C allele. And you perform this over the entire genome and identify regions that are significantly associated with the disease of interest. But the added layer of complication when you have an infectious disease is that you want to actually control for the exposure to the pathogen as well. So you want to have the same epidemiological risk associated with exposure to the disease. I worked on this project that was led by Megan Murray at the Harvard School of Public Health, where she designed a cohort of household contacts of TB cases in Lima in Peru. The study site was in a peri-urban area around Lima called Caraballo. And this is a high TB transmission area, and actually as of last year also a TB COVID high transmission area. And you can see that the housing density is very high, which leads to a high incidence of disease. So in the parent study, we had over 3,000 individuals that were diagnosed with TB disease, so those are the index TB cases. And what we're looking for is the household contacts. So this is a way to control for exposure and make sure that everyone was actually exposed to mycobacterium. And these household contacts were followed up for 18 months. Some of these individuals converted from a negative skin test, so TST is tuberculin skin test, which means you haven't been infected with MTB, and converted to a positive skin test. So that indicates that people have been infected, but they did not develop disease symptoms. So these are the controls. So we know they've been exposed and infected, but did not develop the active disease. And some of the household contacts became secondary TB cases, so they actually developed TB disease. So in our Genome-Wide association study, we included both the primary index TB cases and the secondary TB cases as our definition of cases, and the controls were people who converted from TST negative to TST positive. The first part of the study is published, and if you're interested, you can look at it in more detail. And the question is, how does post-genetic variation confer susceptibility to TB? Can we identify specific regions in the genome that can give us clues about host factors associated with TB? So I worked with Yan Luo, who's based at the Broad Institute in Boston, and she analyzed the genetic data from this Peruvian cohort. We had, in our definition of cases and controls, about 2,000 in each arm. And we identified this one region on chromosome 3 where there was a cluster of variants that were associated with a higher risk of progression to TB. So the lead variant was a single nucleotide polymorphism, or SNP, that showed an odds ratio of 1.18. And people who had the minor allele, which is the A allele, had a higher risk of progression to TB, whereas people who had the dominant allele in the population or the major allele in the population were more protected. So this region actually doesn't fall into a coding region of the genome. It's a non-coding region, so we wanted to understand how a non-coding region was actually associated with progression. So there are several mechanisms by which non-coding variants could regulate, for example, gene expression. This is one example where you have uninfected dendritic cells, and maybe under specific conditions where the cells are not infected or stimulated, the chromatin is similar between cases and controls, where you don't have any gene regulatory activity and no transcription factor binding. However, when you get exposed to a pathogen or a stimulus, this might cause some chromatin remodeling around the transcription factor binding site. And if you have a single nucleotide polymorphism that intersects with this transcription factor binding site, then you might have differential regulation of gene expression. So people who don't have, people who have the C allele in this example would have minimal transcription factor binding, and therefore gene expression regulated by this transcription factor would not be induced. On the other hand, people who have the A allele would have transcription factor binding and not regulate gene expression. So this was our working hypothesis, is that the variants that were sitting in this non-coding region were sitting in an enhancer that was potentially regulating the expression of other genes. So one common question that comes out of genome-wide association studies is how do you identify which cell type to actually start analyzing which genes are regulated by this region. So I worked with Tiffany Amariuta, who was a PhD student also at Harvard Medical School, and she developed this algorithm called impact or inference modeling of phenotype-related active transcription. I know it's a big word, but I'll try to simplify it in this diagram. So the idea here is to look for gene regulatory features that are available in public data sets. So these can be open chromatin, which indicates high levels of transcription, methylation, acetylation, over 500 different gene regulatory databases. And what you would do is correlate these features with transcription factor binding motifs. And since transcription factors tend to be associated with specific cell lineages, especially if it's a master regulator of a specific cell type, we can then infer what cell type this gene regulatory activity was present in. So she would assign a score based on how predictive these gene regulatory features were of transcription factor binding sites, and that's the impact score. And we try, based on the identity of the transcription factors, to assign a potential cellular truth or cellular identity. So Tiffany performed this impact analysis on the region where we identified the genetic variants. And you can see that the lead SNP was actually predictive of a high impact score in monocytes. So we found this transcription factor ChIP-seq data set, which indicates that monocytes are likely to be the cell of interest where there's an active gene regulation. So that led to the hypothesis that this marks a monocyte-specific enhancer region, and then the question then becomes, well, if it's an enhancer in a gene regulatory region, what would be the transcript that would be regulated by this enhancer activity? So to do this, I used the CRISPR-Cas9 technique to disrupt this enhancer, and if you're designing CRISPR knockout experiments for specific genes, that's a lot easier because then you know exactly which, how to actually identify that your gene has been knocked out. But for a non-coding region, the idea here was to introduce a high number of insertion deletions. So, Cas9 is a nucleus, so it would create double-stranded breaks. And when the cell tries to repair these double-stranded breaks, you introduce a lot of insertion deletions. So in order to disrupt this enhancer region, I designed 3 different guide RNAs around the primary SNP of interest. And the idea here is to introduce a high number of insertion deletions so that the enhancer region is disrupted, and therefore we can detect gene expression downstream of the enhancer disruption. So I did this in bulk THP1 cells and chose THP1 cells because we predicted that this activity would be in monocytes. This was the available monocytic cell line. From the bulk cells, then I single cell sorted these edited cells and performed Sanger sequencing around this region to detect the editing efficiency, and also low input RNA sequencing so that we can identify which genes could potentially be regulated by this enhancer. So this is just a snapshot of some of the clones. So if it's blue, that means that the region of interest actually looks like the wild type, so the cells haven't been edited. In other examples, you can see that there are differences between the edited clone and the wild type clone, and in some cases you have these large deletions because we have 3 different guide RNAs in the region. So just looking at it on a gel, you can see that some of the, by PCR amplifying the region, you can see very clear deletions in some of the clones. And some of them have the same size as a wild type clone, but then when you actually look at the sequence, you can identify differences. So I call these edited but not deleted. And then you have the wild type clones which have the same size of the amplicon and also the same sequence. So we performed RNA sequencing on these clones, comparing the wild type and the edited clones, and this was probably the most expensive negative result I ever generated. So we actually could not identify any genes that were differentially expressed between the wild type and the edited clones. And this is actually a common issue in genome-wide association studies, that we could not validate the link between the variant and specific genes. And it could be for multiple reasons. Maybe we did not choose the right cell type, we did not choose the right stimulation condition to actually identify differences between wild type and edited cells. So it took us back to the drawing board, and I used a different data set to try and infer the pathway that could actually be regulated by this genomic region. So I was involved in this study when I was a postdoc in Cape Town, at the University of Cape Town a few years ago. And this is an African household contact study where we recruited TB cases and also household contacts in 4 different regions, so the Gambia, Uganda, Ethiopia, and South Africa. And in a very similar study design, we followed the contacts of indexed TB cases and identified who progressed and didn't progress to active TB disease. So this is just another visual representation of the study design. So you start off from the household contact point, so this is time 0, and follow people up for 2 years. So you can see that some of the individuals would actually develop TB during the course of the 2-year follow-up. And we align them with controls that are matched by age, sex, and the same recruitment region. And what we can do now is align the samples by the time of TB diagnosis and then retrospectively look at transcriptional changes that preceded the progression to TB disease. So this is a unique study design in that you actually have insight into the progression before individuals develop TB disease. And we performed RNA sequencing on whole blood samples. Just for the lab analytical plan, we start with these frozen PAX gene tubes, meaning the sample collection took about a decade actually before I started my postdoc, and extracted RNA samples, and we performed this RNA sequencing experiment where we specifically focused on exon junctions because we wanted to reduce some of the transcripts into real-time PCR assays. One application is to identify biomarkers that predict risk, but I'm not talking about that today. The other application is to actually use this data set to identify mechanisms of progression from infection or exposure to Mycobacterium tuberculosis to active TB disease. So now integrating the 2 data sets, one from the Peruvian household contact study and the second one from the Pan-African household contact study. First, we wanted to get insight from public data sets into what genes could potentially be regulated by the primary SNP that we identified. So this is a chromatin capture data set that's present online, and we're looking at monocytes here. So the idea here of these lines is to show physical interaction between the SNP and promoters of different genes. So you can see that there is a significant interaction between our primary SNP and this gene called ATP1B3. And now looking at the second data set, which was the household contact study from the 4 different African countries, you can see that this gene and also related genes in the same pathway were also differentially expressed between people who progressed to TB disease and people who didn't. So now with the variant information from the Peruvian study and this pathway information that we identified in the African household contact study, we're starting to get hints that ATP1B3 is potentially a candidate risk gene for TB progression. So what's ATP1B3? It's a sodium-potassium ATPase, and B3 means that it's subunit beta 3. There are 4 different alpha isoforms and beta isoforms and another third regulatory domain. And what they do is that they maintain the electrochemical gradient of potassium and sodium. So normally extracellularly we have a high concentration of sodium and a high concentration of potassium intracellularly. So this active process, which is ATP mediated, would maintain these concentration against their gradients. I looked at another public data set of RNA-seq data from monocyte-derived dendritic cells that were infected with live MTB or stimulated with heat-inactivated MTB. And in the short term, it seems that at least the infection or stimulation with MTB leads to upregulation of ATP1B3. So it seems like the upregulation of this gene, based on this data and from the whole blood RNA sequencing analysis, was associated with a higher risk of progression. So the obvious next step is to edit ATP1B3 in THP1 cells, infect them with MTB, and see if there is an association with regulating MTB growth in vitro. So I generated clonal THP1 cell lines that were edited for ATP1B3 or TCR alpha as a control gene. So starting from bulk THP1 cells, I nucleoaffected them with Cas9 protein and 3 different guide RNAs that target ATP1B3. And from these bulk edited cells, now we can sort them out into ATP1B3 sufficient cells that can be used as controls or knockout cells. And luckily, ATP1B3 is a surface protein, and there's a commercial antibody, so we can actually sort the cells based on the expression of the protein. And the prediction if MTB benefits from upregulation of ATP1B3 is that the growth will be lower in MTB-infected ATP1B3 knockout cells. So this is the experiment here. So I sorted 60 positive and 60 negative clones based on the expression. So the editing efficiency was about 50%, so we can immediately sort cells that express ATP1B3 and cells that don't as controls. And expanded them for 6 weeks and then validated that they maintained the expression that was predicted from the initial sort. So you can see that there are cells that were expressing high levels of ATP1B3, which were predicted based on this, and then the cells that are ATP1B3 negative. Now to address the question of whether the ATP1B3 deficiency would impact MTB growth in vitro, we use these MTB lux reporters, which allow us to actually measure MTB growth by measuring luminescence. So the advantage of using this over traditional CFU experiments, where you actually have to count MTB from each well, is that you can just measure it by a plate reader and just look at the luminescence. So this is preliminary data that suggests, so just guiding you through the experiment here, these are the days post-infection and the different THP1 clones. So we had the TCR alpha guide RNA treated cells in black, so that's a control. And then another control is the ATP1B3 positive cells in blue. And then our cells of interest are the ATP1B3 deficient cells. So at least on a preliminary level, it suggests that indeed ATP1B3 deficiency results in lower MTB growth. So MTB benefits from higher ATP1B3 levels. Experiments to validate what this actually means and whether their mechanisms are still ongoing. So one hypothesis is that by deleting ATP1B3, you actually reduce potassium efflux, which is a driver of inflammasome activation. So this is one working hypothesis that we're currently testing. So another way to formally integrate variants and gene expression is to conduct what we call an Eqtl study. So I'll explain that very quickly. So in this study design, we used the same cohort of people from Peru that were TB patients and household contacts. And now we're recruiting them years later after the initial parent cohort was recruited. So we had this sub-study where we enrolled about 70 cases and controls. And because this was nested from a genome-wide association study, we had the genotyping information for all the participants in both arms of the study. And what we did is take the cryopreserved PBMC samples and then enrich for CD14 positive monocytes. Again, following the theme of focusing on innate immunity, the monocytes were differentiated into dendritic cells using this cocktail of cytokines, so GM-CSF and IL-4, or macrophages using MCSF. And we performed RNA sequencing on both the dendritic cells and macrophages, and because we had the genotyping information, we could integrate the two data sets to identify regulatory events. So just as a quality control, we can see that the samples that were sorted as dendritic cells showed the transcripts that we expect to see in dendritic cells. So we have genes like CCL17 and 22, group 1 CD1 genes, and the macrophages show the genes that we expect to see in macrophages like Fc gamma receptor 1, and they also maintain high levels of CD14 as opposed to dendritic cells. So that gives us the green light to move to the next step. But when we try to look for genes that are associated with TB status, remember these are people who progressed to TB 5 years ago, so we could not identify transcripts that were directly associated with TB disease just by looking at the RNA-seq data. But now we have the genetic data to also integrate with the RNA-seq. So the analysis is called an expression quantitative trait loci analysis, and this is just a fancy way of saying you want to look at associations between different genetic variants and gene expression levels. So you can see in the example on the left, whether you have the G allele or the T allele, there's no impact on gene expression. But in the example on the right, you can see that based on your allelic variant, you can see that the TT genotype was associated with higher levels of this gene of interest. And similarly to what I mentioned earlier, this could be because you're disrupting a transcription factor binding site or an enhancer element that regulates specific genes. And I've been working with Maria Gutierrez ourselves, an assistant professor at Harvard Medical School. So we have two unique questions to ask. One, are there cell type specific EQTL events? So are genes regulated differently in dendritic cells and macrophages? And also we have the disease association. So are there events that give us insight into that give us insight into genes that are regulated differently in people who have TB versus the people who didn't? And the primary analysis showed us that there are 433 DC-specific events and 355 macrophage-specific events. And out of these, 79 were actually unique to one cell type, so present in DCs but not macrophages or vice versa. And the top macrophage-associated gene was Gizdermin A, which is a pyroptosis-associated gene. So you can see here that people who had the homozygous minor allele had lower expression of Gizdermin A in macrophages, but not in dendritic cells. And on the other hand, the top DC-associated gene was CD1A. So we can see here that people who had the minor allele had lower expression of CD1A. So back to the primary question, which is, are there any associations that give us insight into TB progression mechanisms? So we applied this complicated linear regression model that basically looks at association between gene expression and genotypes, but then we include a number of other covariates, so TB status, age, sex batch, and these expression principal components basically just reduce the noise in the data so we can identify real events and reduce the noise. And the term that we're interested in is the interaction between the genotype and TB status. So separating the progressors and controls, we can now see that in DCs, the top hit was this association between this variant and FAH expression, and I'll talk in the next slide about what FAH is. But the cool thing is that this was associated with TB status, but was also a cell type specific association, because we see this in dendritic cells, but we don't see it in macrophages. So FAH is fumarate acetoacetate hydrolase. It's the last enzyme in tyrosine metabolism. So it breaks the semifinal product fumarate acetoacetate into fumarate and acetoacetate. Loss of function mutations are associated with this genetic disease called hereditary type 1 hypertyrosinemia. And there isn't actually quite a lot of literature on the association between tyrosine metabolism and TB infection, so this is an interesting hit to follow up on. And analyzing the same RNA-seq, the public RNA-seq data set of MTB infection of monocyte-derived disease, the acute infection shows that FAH is downregulated in response to infection. So this suggests that MTB infection could potentially benefit from downregulation of FA, which would block the last step of tyrosine metabolism. So we're working now on identifying whether there's also an impact on MTB infections in vitro and what this pathway actually means and trying to identify the mechanism. So in summary, risk of TB progression can be a heritable trait. It's more difficult to mine GWAS data for infectious disease studies, as I mentioned. So trying to have a control study where you know exactly that exposure to the bug is similar between cases and controls increases your confidence that you're identifying real hits. But the functional validation of these risk loci is very important. And one challenge is identifying what the pathogenic cell subset is. And you know, we have studies where we only look at genetics or we only look at transcriptional data, but integrating two data sets, either by looking at two data sets from two different cohorts or integrating them in the same data set, and I've shown you examples of both, give us novel insights into disease mechanisms, which are exciting to follow up on. So with this, I would like to thank my former mentors at Harvard Medical School, Branch Modi, Ildipo, Shoma, and Megan, and a number of people acknowledged across the slides, Maria, Kathy and Sarah Iwani, and Melissa who performed the BSL-3 experiments, and my former colleagues in Cape Town who helped with the Pan-African household contact study. So, happy to take any questions.
Okay, let's give just want to just one burning question to one just burning question to the speaker. None. Okay. So so we have we can share those questions with you. And sure. So thanks so much. Sorry for keeping you late in the night.
Oh, it's fine. I wish I was there with you in person.
All right. Thanks so much. Let's give a final applause. Because we have one speaker who joined us via Zoom from Chile, Dr. Kennedy. Yes, so Dr. Josiah Kuja, you'll come last so that we don't have to reconnect and connect. Apologies for that. But you are my brother, we can sort it out over beer. I'd like to introduce the next speaker, Dr. Kawashima. He's a postdoctoral fellow in Japan Society for the Promotion of Science Research Fellow in Graduate School of Engineering at Chiba University, Japan. He received his PhD in engineering in Tokyo Metropolitan University 2017. His background is in mechanical engineering, especially in heat and mass transfer engineering, in mini and microscale channel with spectroscopic and imaging analysis. His current research interest focuses on electrical impedance, spectroscopy, and tomography applied to the cell biological analysis, medical diagnosis, and industrial process inspection. Please let's join us in welcoming Dr. Kawashima from Chiba University, Japan.
Thank you, Chairman. Can you hear me?
Yeah, we can hear you.
Can you hear me?
Yes, go ahead.
Okay. Can I speak?
Yes.
Okay, let me go ahead. Okay. very honored to be able to present my research in this conference. And also thank you for giving me the opportunity to talk here. So today, my topic is about electric impedance spectroscopy and tomography. We call it EIST, and its application to cell measurement and evaluation, and also visualization. So, electric impedance spectroscopy with EIST can visualize the cross-section of target materials and objects using the electrodes. It's a similar technique to the XACT, which is used in the medical diagnostics, as you know. So EIST provides not only images but also the spectroscopic information about the target materials. So therefore, EIST is also useful for structural analysis. And the advantages of the EIST are the non-invasiveness, low cost, ease of use, and safety comparing to other modalities such as X-ray. So as you can see in these photos and the videos, EIST can be applied in many fields. Most of them are applied in industrial applications such as energy plant and chemical reactor, that's shown below. But now we are trying to apply this EIST technique to the biological measurements like lymphedema, thrombosis. And today, I will talk some measurements related to the ion channel. So this cartoon demonstrates the concept of the cell measurement associated with the ion channels. And as you know, the ion channels have many types within the potassium channel, and which play a role in the maintaining the conditions of cells, tissues, and the human body. In addition, the transmembrane ion transport via the ion channel is closely associated with the cell conditions. For instance, the differences in the intercellular contents and cell types, tonicity, pixels, and so on. So because the transmembrane transport, there are changes. Therefore, we try to measure the ion transport. The transmembrane transport for painting the cell conditions. This cartoon shows our initial study of cell measurements associated with the ion channel. In this study, we evaluate the transmembrane ion transport using the spectroscopic part in EIST. Setup is very simple. We use the impedance analyzer and the flux sensor, and they are controlled by the PC. It's very simple. Then we place the cell suspensions here on the electrodes. Then we measure the impedance spectra over time during transmembrane transport the ion channel. The point of this measurement is to use the low frequency current, because the low frequency current may pass through the extracellular solution, avoiding cell membrane, which reflecting the ion concentration in the extracellular solution. On the other hand, the high frequency actually pass through the solution and the membrane, so it's reflecting the liquid and stuff. So we use the low frequency current mainly. This is the measurement protocol. So actually we replaced the DMEM as the cultural medium with the deionized sucrose using the centrifugation 2 times, because the transmembrane ion transport from intercellular to extracellular solution was artificially realized. After replacing the medium, we placed the cell suspension on the electrodes, then measured the impedance of the time during the ion transport from the cells. In this experiment, we used the 3 types of cells, which is the wild type WT, HT, and DHPT. Those three cells are derived from the MRC5 cell, which is human fetal lung fibroblast cell lines. Now, compared to wild type, the HT modified the nucleus area, in which green fluorescent protein GFP was expressed. Also, the histone 2B is here, but is overexpressed compared to wild type. And in GFPT, the GFP is expressed in the cytoplasma rather than the nucleus. So actually the GFP has negative charge, so which can affect the transmembrane ion transport. The results show the opposite. This graph shows the nitric skull on the left here. So it shows the change in the electric characteristics of the suspension. Actually here is low frequency, but then here is high frequency, but we plot it like this over time. Yeah, actually this like a semicircle is the diameter is decreased over time, which is reflecting the ion concentrations improvement in the extracellular fluid. So especially in the low frequency path. So by using this low frequency impedance, we can convert it into the conductivity change, which is directly reflecting the ion concentration in extracellular fluid. So here, we can show you can see the conductivity is dramatically increased fast and the slightly increased after that in each cell types. So the difference is not so big. So in order to understand the transmembrane ion transport phenomenon among these three cells, we try to analyze ion transport analysis. So this is the flow chart of the transmembrane ion transport analysis, especially in modeling. So in the modeling, we consider the extracellular region as the calculation region here in this model. We assume that ion movement is based on the fixed law of diffusion as governing equation here. And also we assume the flux of ions is regulated by the transmembrane coefficient here. In the we assigned it in boundary conditions. By comparing the here's the experimental and here's the modeling, and from the experiment we can obtain the concentration. Also in the transport model we can obtain the concentration for the modeling. So we compare each other, then the minimization process using. Then the optional, if it's minimized, we can obtain the optimal E, the transmembrane coefficient. So in the left part, this graph shows the results of each cell type. As you can see, the cell type shows the significant difference in the transmembrane coefficient P, so which indicates that transmembrane ion transport is sensitive to the intercellular conditions. And next part, I'd like to explain the different aspects about this. In this case, we consider the tonicity. The tonicity is defined as the effective osmotic pressure, especially when considering the swelling or shrinking response of cells by water permeation via the membranes. In our experiment case, tonicity can be affected by the solution concentration. In an isotonic condition, the equilibrium of water flux is maintained, so net flux of water is there. However, in the hypertonic and hypertonic conditions, the net flux of water is non-zero, which means that the cells are swelling or shrinking. The size is changing. That's why the tonicity imbalance also increases the transmembrane coefficient. This is the also the outcome, actually the same as the previous research. So we just replace the media with the ionized solution. But in this case, we change the cross concentration and 7 conditions. And according to the cell size comparison with the culture conditions, the 50 millimolar cross concentration shows the isotonic condition. Lower than the 50 means the hypertonic, and larger than 50 means the hypertonic conditions. Then we also show the calculus, the transmembrane coefficient using this data. So in this case, the transmembrane coefficient P was obtained. Yeah. Then compared to the isotonic condition, the other 2 cases, two conditions show the higher transmembrane coefficient. Maybe it's due to the activation of the osmolarity sensitive or mechanism sensitive ion channels. So that's why we think the transmembrane ion transport provides the cell conditions such as intercell condition and tonicity. Very useful information. And recently we are also trying to apply this technique for the imaging technique using the EFSP, electric impedance spectroscopy. This video demonstrates how EFSP works with it. So as you can see here, we measured impedance at the boundary of the object. Then, but we measured the impedance multiple pattern of impedance using this 8 electrodes combination. Then we can reconstruct the image as cross-sectional areas. So here, he takes the acrylic rod as non-conducting materials. If he moves the rod, instantaneously visualize where the rod is by using this system. So to apply this technique to the ion concentration dimension, so we developed and miniaturized the new sensors based on the printed circuit board. In this case, the H electrodes were printed and the coaxial connectors and was like this. Using this sensor, we also apply the transmembrane ion transport. So this graph shows the setup. Mine is very similar to the previous experiments, but the difference is in we use the multiplexer switching of electrodes, and we use these new sensors. And in this experiment, we also use the MRC part cells, but we use the spheroid. We make the spheroid. So after making the spheroid, we place the spheroid on the center of the sensor and injected the diamond square solution and visualize ion concentration distribution over time during the transmembrane transport via ion channels. So this is the final image. This movie shows the ion concentration. Actually, it's the conductivity, but it's directly reflecting the ion concentration around the cell spheroids. So we can successfully visualize the ion concentration around the cell spheroids. Now it's still under analysis and considering how we can evaluate this transmembrane ion transport on this image. But we believe this technique is useful, these measurements, and also we want to try to apply it for the drug discovery research and development. Finally, I would like to thank my colleagues, students, and collaborators for supporting this research. Thank you for kind attention.
Thank you. Thank you so much. One burning question? Okay. They are good. Thank you so much, Doc.
Thanks.
Yeah, thank you.
Well,
Yeah, thank you very much.
all right. So the next speaker will be Dr. Our last speaker this morning, and we are running late. Dr. Josiah from Jomo Kenyatta. Why am I thinking you're from Jomo Kenyatta University? It's a sort of and the College of Graduate Studies and Research at Mount Kenya University, a bioinformatician with a background in molecular microbial ecology. For sustainable development and shared prosperity. Let's join hands in welcoming Dr. Josiah Koja for this presentation.
So thank you, Professor Collins, and I confirm as far as introduction is concerned that what we said is true. So I'm a postdoc at the College of Graduate Studies and Research, and also teach at the Genome-Wide University. So I want to talk about genomics and bioinformatics as a resilient approach to climate change, disease epidemiology, and as well as conservation of threatened biodiversity. Today I'll speak about Africa, because Africa, we have to move. So now here we have students, the postgraduate students and undergraduate students who are working on biological samples, some doing molecular work with the intention of sequencing, but always we clear our studies and celebrate, dance, and go home. But we have a way, and we can proceed in research and appreciate science. Thank you. So, genomic trends in Africa, and this is what you have. So these are just the sequencing devices that are present in Africa. And it's so much skewed to South Africa, where there were 78 devices for sequencing. And this is closely followed by Kenya at 28. You have Egypt 24. Nigeria also comes in at 14. Morocco as well, coming at 18. The problem is that we are so much into research for ourselves as Africa, and we have research groups in Africa, working on human genetics and related diseases, as well as environmental genomics, applies to plant genetics and animal genetics with a focus, but we are forgetting to focus on the African genetic studies, because at the end of the day, we are working with genetics. That must be in database, because it's very sad that if you look at the African plants, less than 3% are in the national database for reference. Similar applies to animals and also those related to human genetics. So there is a need to move together, work and share it. 8th of July, August, there was the report from the Intergovernmental Panel for Climate Change talking about the increase of carbon emission to the atmosphere. And mostly the Intergovernmental Panel, they are focusing on the human activities and industrial production. And microbes, the microbial world is not so much pronounced. So scientists, government and scientists need to work together so that to make a conclusive communication as far as management and zero carbon is focused, because microbes will play important role in climate change since they have interaction with plants, animals, and as well as human in the entire environment. Again, these microbes are very important, and their impact on climate change as well is forgotten, because your microbes, the methanogens, which play and produce so much to the atmosphere. On the other hand, these microbes can be used in industrial management for biotechnology and production. However, so they must support life forms, and they shape the response to climate change in the production of methane, as I was said. There is need for integrated research in microbial world. So as I have said, the government has already gone. He was here. I believe they are affiliates with the government, Dr. Nyambege. Okay, so I was happy when he was talking of biotechnology, food production, cancer development and establishment. There is need for cooperation among the African institutions, the government and the scientists. Scientists should not just stay in the institutions, but they need to really participate in the development of government policies as far as climate change and the impact are concerned. So I met scientists from Austria in a conference in Hokkaido, North Japan, 2017, on glacial biology. And when I presented, they talked of their geologists that they've been studying the African glaciers. And they told me, why can't you study the dynamics of microbial ecology along the Lakes Glacier? Because this glacier in Mount Kenya lies along the equator. So it means it is so much exposed to climate, to heat, radiation, and global warming. So, and this glacier has been studied. These are all the way since 1934, the blue mark, and the white mark that is now in 2010. And after sharing with the geologists, we came for our mapping. And the problem is that the glacier is disappearing. It means the biodiversity is disappearing. So 2010, the glacier was there connected. In 2016, there's a rock already. And now if I say what is there, is that a patch of glacier for evidence. So we'll talk about this glacier, our study, which focused on the upper side of the glacier and the lower side. So this, the upper side is separated by a rock with the lower side. So upper side is a bit flat, while the lower side is a bit slopey. Then I will talk of four field or four land. The four field of four land is where the glaciers disappeared. So my work, what I did is to compare the differences in the far field where the glaciers disappeared and the glacier content. So I did the 16S for metagenomics, and with 34 samples, and the difference comes in the relative abundance of community structures. The community structures within the glacier. So the first red are glacier, upper glacier, remember, upper glacier. This is lower glacier, the blue. The purple ones are the far field. And the black ones are also the side far fields. So here is cyanobacteria. This is upper glacier, lower glacier, with higher abundance of cyanobacteria. When you move to the side far field in black and the far field in purple, I believe that's purple, we can see disappearance of cyanobacteria. Just some element at the primary clearing site. So there is an activity taking place when the glacier disappears and leave dry land. So cyanobacteria is the primary producer of the glacier. But when there is disappearance, it means it also disappears with the glacier as melt water. So this alone indicates a change in biodiversity, that as we lose our biomes or ecosystems, then as well we are losing the biological samples which can be conserved for future references. Again, this is a heat map showing cyanobacteria being so unique on the glaciers. And it is here outstanding because it is more on the glacier and not on other sides. So here you have the dendrogram for the glacier, upper and the lower glacier, and cyanobacteria is there, abundant on the clusters. So this relative abundance is also supported by the principal component analysis, in which we have lower glacier, the foreland is brown, and the upper is the cross. So samples or the taxa, they cluster together. It means they belong to themselves. So as you lose the glacier, you lose specific organisms that could have really been played, because the glaciers exist at a maximum of 4 degrees on the equatorial alignment. So these are prime samples that can be used in industrial development. So that is metagenomics within the environment. Now, in disease epidemiology and its application, we continue to experience different outbreaks, and presently we experience the pandemic of COVID. And there is a need for surveillance, for identification of the outbreaks at early stages, since this is very important to contain the spread of antimicrobial resistance organisms. Identifying the sources of pathogens and their transmission pathways is really critical in the implementation of preventive measures and also containing the spread further to other populations. Molecular genotyping of bacterial isolates is very important in the determination of extent and sources of outbreak resulting from the antimicrobial resistance. Now, based on the conventional approaches of genotyping, they are overwhelmed and there's need for intervention. And the intervention only comes for the next generation sequencing. And the need is to develop protocols that can be used within short period, within short turnaround times, ready to respond for cases of outbreaks. So conventional genotyping methods rely on selected genes or biomarkers for the whole genome sequencing. And this really makes them so inadequate because they're so specific to respond to an outbreak. Develop rapid and more accurate NGS protocols for surveillance and outbreak investigations for antibiotic resistance microbes is essential. NGS allows, the good thing with NGS, next generation sequencing, is that it allows for the discriminative analysis among isolates of the same lineage, and we can use the differences in the single nucleotide polymorphs or the index for the classification. And currently, that's where the focus is at the Gitaka lab, where we are working on a real-time outbreak investigation protocol to conduct rapid tests for environmental antimicrobial resistant genes. So, I know you always say, where can we work, where can we reach out to these bioinformatics and genomics. Okay? And Africa, there's a solution for you. So there is a project called African Genome Project. And the focus is on genomics and conservation. This project majorly is focusing on the non-human genomes sequencing, but it's in affiliation with the like the H3A Bionet for the health hereditary diseases, and also the 54 genes, which is looking for the precision medicine. So African Biology Project is a platform that offers experience for students, young scientists, to participate in genomics and bioinformatics for the future of Africa. The aim is for sequencing for a sustainable development and shared prosperity. So these are some of the goals of the African Genome Project: to coordinate research processes, also to initiate and develop support for staff capacity building, and this will really bring active African researchers together. So what I want to say is that if you want to join the genomics and bioinformatics for the African Genome Project, you can just Google African Genome Project, then you do a Google form. I will receive the communication and get back to you. In conclusion, genomics and bioinformatics studies are resilient approaches to understand climate change and its impact. And when I talk of glacier, it's not only glacier where you can work. Because climate change affects even human health, we have effluents from the industries. We need to understand what will you interact with the environment. So genomics and bioinformatics is the key to follow. NGS is a promising approach for the validation of disease outbreak, surveillance, and epidemiology for communications and policy formation. Genomics and bioinformatics are very essential in conservation for shared prosperity, especially in the raw resource centers. So genomics and bioinformatics are very important. And Dr. Nyambega, please tell the government representative to ensure that there's precision medicine in the Jaramogi Hospital for collaboration and work.
I will.
Otherwise, thank you. So here my great mentors, the upper lane, some of them are very noisy. And the research team at the Eqtl lab are also here. And I appreciate them. Thank you very much.
Thank you, Dr. Kuja. Now you know where to go if you want to do bioinformatics and genomics locally. Any burning question? Just one? Looking around, none? Okay, we are good. So let's give him a final applause. Thank you so much. This brings us to the end of the first session. We know we took too long, but apology for the time lag because of other technicalities. I'm kindly requesting that before we go for the tea break, we assemble outside there and take a group photograph. I don't know how that will happen because we are over 150. But they've assured us they can take a group photograph very quickly so that we can capture this moment and keep it for our records. Then you can quickly go for tea break, which will take around 20 minutes because there are several
several summing points, and then we'll get back here for this next session. And let's clap for in the morning for all our speakers about it. Thank you so much. And let's meet outside for the group photo.